Okay, second example about the divergence theorem for computing flux. Here's a reminder of what the divergence theorem says. Flux equals a triple integral of the divergence, and divergence was this formula. It's a scalar field, and so now we want to use the divergence theorem to find the flux of this vector field across the surface, which is the sphere. So again, for the divergence theorem, you choose a normal vector which points away from the surface, or from the interior of the surface, and the interior of the surface in this case, since the surface is a sphere, is like a ball. Okay? Now the point is that doing this double integral is a bit more tedious because you have to find a normal vector in sphere, for a sphere, and I mean that can be done using a parameterization, but it's a bit boring. On the other hand, here it's more straightforward because you just have to find, according to the divergence theorem, this will be this triple integral over this ball of the divergence of f dv. But what's the divergence of this? Well, this would be 2 plus 2y plus 2c. 2 plus 2y plus 2z. And again, now let's write this, sorry, I forgot dv. And let's do the integral. This is the integral of a ball. So let's do it. This is from 0 to 2 pi, 0 to pi, 0 to 1. Remember that in spherical coordinates, y becomes rho sine of phi sine of theta, and then z becomes 2 rho cosine of theta, sorry, cosine of phi, rho squared sine of phi, d rho, d phi, d theta. So we just have to do this triple integral. And so this is, again, integral from 0 to 2 pi, 0 to pi of, let's see, so you're doing 2 rho squared, I mean, let's do it, you're going to integrate first with respect to rho. So this gives you 2 rho squared. So that gives you rho cube, 2 rho cube over 3 plus times sine of phi, right? Oh, everything is being multiplied by sine of phi, so well, let's write it like this. Now this one gives you 2, so this gives you rho cubed, so it becomes 2 rho to the 4 over 4, and then this is sine squared of phi sine of theta, plus, again, this is 2 rho to the 4 over 4 sine of phi cosine of phi, and now all of this has to be evaluated at rho equals 1, rho equals 0, rho equals 1, rho equals 0, rho equals 0, rho equals 1, and this is, after you do the evaluation, this is d phi d theta. So this gives you the integral from 0 to 2 pi, integral from 0 to pi of 2/3 sine of phi plus 1/2 sine square of phi sine of theta plus 1/2 sine of phi cosine of phi d theta. And again, if you want, we can do the trick of integrating first with respect to theta. the point of integrating first with respect to theta is that the integral of this term will go away because sine of theta from 0 to 2 pi gives you 0, and everything else just gets multiplied by 2 pi. So you just get 2 pi times the integral from 0 to pi of 2/3 of sine of phi plus 1/2 sine of phi cosine of phi, all of this being integrated against the phi. And now integral of sine is 2 pi times 2/3 negative cosine of phi from at pi and 0. And then, well, you can do this with a substitution. This is like sine squared of phi over what? 4. Yeah, phi equals 0. At pi and 0. This one goes away because sine at pi and 0 is 0. And this gives you negative 1. Negative, like gives you 2 because it becomes minus 1, which is 1. And then minus, and then plus 0, plus cosine of 0, which is 1. So this gives you 2. So you get 2 times 2, that's 4 times 2, 8. So you get 8 pi over 3. Okay, and so that's the, again, another computation of flux using the divergence theorem.